Hi everyone, today we're going to study reliability. Reliability plays a vital role in almost all branches of engineering disciplines. Generally, the reliability of a component or a system is its capability to function without breakdown or failure. If a system or a device performs better, it is considered to be more reliable. In a broader sense, reliability is associated with dependability and durability with successful performance without any malfunctioning or failure. Technically, reliability may be defined as the probability that a component or a system will perform properly for a specified period of time t under a given set of operating conditions. In other words, reliability is the probability that the component does not fail during the interval from 0 to t. Let us study reliability function. Suppose that a component starts functioning from a specified time, say t equals 0. And if capital T is the time until it fails or ceases to function properly, then capital T is called the life length or time to failure of the component. Clearly, capital T is a continuous random variable with some probability density function f of t. Then, the reliability function of the component at time t is denoted by capital R of t. Now for the formula, we say that capital R of t is equal to the probability or P when capital T is greater than small t. By definition, the right side becomes 1 minus capital P of when capital T is less than or equal to t. And this probability when capital T is less than or equal to t can be simplified into capital F of t. Remember that this capital F of t is the cumulative distribution function. So this is our formula for reliability function. Now, if small f of t is given, remember that this capital F of t is equal to the definite integral from 0 to t of small f of t dt. So this value of f of t we can substitute in here. So the formula becomes 1 minus this definite integral. So we have this second formula. Consequently, given the reliability function capital R of t, the probability density function, the f of t formula is this small f of t is equal to the negative of derivative of capital R of t. Let us see this simple example. The failure distribution function, and this is capital F of t of a building system, is given by capital F of t equals 1 minus e raised to negative t over 100, where t is in years. Determine the reliability function capital R of t. We note that the given here is the capital F of t, and this is the value. So we will use our formula. Capital R of t is equal to 1 minus capital F of t. Substituting the value for this capital F of t, the formula of R becomes like this. 1 minus the quantity, 1 minus e raised to negative t over 100. When we remove the grouping symbol, we change the sign of the terms inside the grouping symbol. So we have this 1 minus 1 becomes 0, and this negative e becomes positive. It means R of t is equal to positive e raised to negative t over 100. This is now the final answer. Today we're going to study hazard function of reliability. Another quantity that we are interested in is the rate of failure of units. This is estimated by the so-called hazard function, denoted by h of t. Hazard function is also called instantaneous failure rate function. It indicates the proneness to failure or risk of a unit after time t has elapsed. However, it is not a probability, meaning it can take values greater than 1. Now this is the formula. H of t is equal to small f of t over capital R of t, where this f of t is the probability density function, while R of t is the reliability function. So we have our first formula here. There is a second formula that we're going to use when R of t is the only given in the problem. So the formula will be h of t is equal to the negative of derivative of R of t all over capital R of t. Let us discuss the bathtub curve. We have an x and y axis. Our x-axis corresponds to time, and the y-axis corresponds to the failure rate, or the h of t. This is the bathtub curve. This is divided into 3 parts. The first part here is what we call infant mortality. The second part, or the middle part, is what we call the normal life. And the last part is what we call wear out period. It should be noted that in reality, an item's hazard function or instantaneous failure rate is unlikely to remain constant throughout the majority of its lifetime. Most items age gradually throughout their entire life, then suddenly starting to deteriorate towards the end, as implied by the bathtub curve. Let us have this cumulative hazard function. The cumulative hazard function is defined from the hazard function as capital H of t is equal to the definite integral from 0 to t of the function h of t, this is small h of t, dt. This cumulative hazard function is associated with the reliability function as the R of t is equal to exponential of negative capital H of t, or the capital H of t is equal to the negative ln of capital R of t. Let us see this example. The failure distribution function, or capital F of t, of a building system is given by capital F of t equals 1 minus e raised to negative t over 100, where t is in years. Determine the hazard function h of t. Our formula for h of t is equal to the negative of r prime of t over r of t. So for step 1, let us compute for capital R of t. Given the f of t here, we have the simple formula r of t is equal to 1 minus capital F of t. This value of capital F of t is given here. Let us substitute this value in the formula. So it will be like this. Then let us simplify the right side. Let us remove the grouping symbol and change the sign of all the terms inside the grouping symbol. So it will be 1 minus 1 becomes 0, and this negative here becomes positive. Therefore, the r of t is equal to positive e raised to negative t over 100. Step 2, let us compute for derivative of r. So it will be like this. R prime of t is equal to this exponential e raised to negative t over 100 times the derivative of this negative t over 100, and that is negative 1 over 100. Simplifying this, we have this negative 1 over 100 times e raised to negative t over 100. Let's proceed with step 3. Let us substitute the corresponding values to our formula h of t. The numerator is the value from step 2 and the denominator is the value from step 1. So it will be like this. H of t is equal to the negative of the quantity negative 1 over 100. E raised to negative t over 100 all over e raised to negative t over 100. This negative and negative becomes positive, so we can rewrite our formula into like this. Simplifying further, we can see that this e raised to negative t over 100 is common in the denominator and numerator, so we can cancel the expressions. So the final answer for h of t is 1 over 100. Note that we can say that the system has a constant failure rate because there is no variable in the answer. Today, we're going to study mean time between failures. The mean time between failures, or MTBF, is a concept which is frequently used in reliability work. It is defined to be the average or expected lifetime of an item. Alternative notation is capital E of t. Then from the definition of a mean or expected value, we have this formula. MTBF equals the definite integral from 0 to infinity, the variable t times f of t, then dt. This f of t is the probability density function. Alternatively, we have this formula for MTBF equals the definite integral from 0 to infinity of this quantity 1 minus capital F of t, then dt. This capital F of t is the cumulative probability function. We most commonly express the mean time between failures in terms of the reliability function. Namely, this is the formula. MTBF equals the definite integral from 0 to infinity of capital R of t, dt. These are the three formulas for the mean time between failures. Let us see this example. Determine the MTBF of the failure density function f of t is equal to 0.2 minus 0.02 t, where t is between 0 and 10, where t is in years. Let us write our formula for the MTBF. So this is about the small f of t. Substituting the corresponding values, we have now like this. MTBF is equal to the definite integral from 0 to 10. And this is the variable t times the value f of t. We have this value and we substitute it here. Then dt. Let us simplify first by getting the product of this variable t with the function f of t. So we have now this 0.2 times t minus 0.02 t squared. Now let us do the integration. This 0.2t becomes 0.2 times t squared over 2 minus this function here becomes 0.02 times t cubed over 3. Then we will evaluate this from 0 to 10. So it becomes like this. The first group is about this function and the variable t is changed into 10. Minus the second group, this same function where t is replaced by 0 respectively. Look at the second group. Because of the 0, all of this becomes 0. Let us simplify the first group only. So we have now this 0.2 times 100 over 2 minus 0.02 times 1000 over 3. Simplifying each of the fractions, we have now 10 minus 6.7, and the difference is 3.3. And we say that this is in years. It means the mean time to failure of the item is just over 3 years. This is the final answer. I hope you learned something from this video. See you again next time.